There are objects in the universe so immense, so powerful, they stretch the very limits of imagination. A place where gravity doesn't simply pull you. It reshapes what reality even means, where time slows to a crawl, until a human second feels like something from another life, where light, the thing we trust most, the messenger that carries information at the speed of thought, is trapped, torn from its freedom, dragged into an endless spiral. And this is not a story about a legend. This is not a fantasy from a movie. This is a real astronomical object, far beyond anything we can visit, but close enough for us to observe, to measure, and fear in the only way the cosmos allows, through its light, through its shadow, through its effects on the fabric of the universe. And its name is TON 618. The strange thing about TON 618 is that it didn't begin with fireworks. It began with a whisper. In 1957, astronomers at the Tonantzintla Observatory, an observatory in Mexico, were mapping the sky, recording objects that looked unremarkable at first glance. They were cataloging faint sources one by one, as humans have done for centuries. Point a telescope, capture a spectrum, record a position, and move on. In the night sky, TON 618 sat near the border of two constellations, Canes Venatici and Coma Berenices. If you had looked only with the naked eye or with the earliest instruments, you wouldn't have noticed anything special. TON 618 appeared like so many other distant smudges, an extremely faint, bluish source of light. Just another object waiting to be understood. Just another entry. Just another number. And for a long time, that's exactly what it was. But the universe never reveals its secrets all at once. Sometimes it hides a monster behind something that looks almost ordinary. And sometimes, the moment we finally learn how to read the light correctly, everything changes. Decades later, astronomers use more advanced methods, especially spectroscopic analysis, to break that faint glow into its component wavelengths. And that's when the truth surfaced, because this wasn't acting like a star. Stars don't create the kind of signatures that TON 618 produced. Stars don't flare with that kind of energy. Stars don't behave like an engine. TON 618 was not merely a single object shining alone. It was the brilliant, furious heart of a faraway galaxy. A galaxy powered by something so dense and so extreme that it could only be explained by one thing: a supermassive black hole, millions of billions of times more massive than anything we see in our own corner of the universe. Now, here's where TON 618 stops being just an object and starts becoming a time capsule. TON 618 lies roughly 18 billion light years from us. Let that number sit in your mind. Light left it and traveled for an unimaginably long journey before it reached our telescopes. But there's an extra twist. One of the reasons this object feels like time travel rather than simple astronomy. The universe is expanding, so distance is not just a static measurement. It's a consequence of how space itself has stretched over billions of years. Because of that expansion, the light we see today began its journey when the universe was much younger, when it was less than a quarter of its current age. That means the photons arriving from TON 618 started their trip during an era when galaxies were still forming themselves at full speed. An era when matter clumped, collapsed, merged, and ignited, when the first generations of stars were lighting up the dark, when the universe was still learning how to become a place where complex structures could exist. So when we observe TON 618, we're not just looking far away. We're looking back into a period of history, a raw, early chapter of cosmic evolution, a time when the universe was energetic, chaotic, and hungry. If TON 618 is powered by a black hole, you may be thinking, but black holes don't shine. And you'd be right. A black hole itself is dark. It doesn't emit light the way stars do. So what are we seeing? We are seeing what surrounds it. We are seeing the violence around the abyss. I in the case of TON 618. The black hole is surrounded by a swirling structure of gas and dust, matter that is being pulled in by gravity. As the material spirals inward, it forms an accretion disk, and this disk is not calm. It's a raging, magnetized storm where particles grind against each other. Speeds increase, temperatures rise, and energy is released across the entire electromagnetic spectrum. This is the key. The black hole turns matter into energy, not by magic, but by physics so extreme it looks like magic. As gas falls closer, it accelerates. Friction and turbulence heat it. Magnetic fields become tangled and snap into new configurations again and again. The result is radiation so intense that a quasar can outshine not just a star, but entire galaxies. Ton 618 is classified as a quasar, one of the brightest, most powerful types of active galactic nuclei in the universe. Quasars are cosmic lighthouses, not because they are gentle, but because their brightness is the byproduct of extreme accretion and extreme energy release. TON 618 is among the most luminous quasars ever observed, so bright that we can detect it across vast cosmic distances, like seeing a lighthouse on the edge of the ocean while standing on another continent, watching the beam sweep across the sky. Except this lighthouse is powered by gravity so intense it bends the rules of physics. And then the quasar reveals another weapon. Jets, magnetic fields amplified and organized by the swirling motion of the accretion disk, can channel energy outward along the black hole's rotational axis. This launches relativistic jets, streams of plasma moving at speeds close to the speed of light. These jets can extend for millions of light years, carving to the surrounding medium like cosmic drills. Now imagine this. Not only is a quasar blasting radiation in every direction, it is also throwing matter outward in narrow beams with enormous power. This matters because the jets aren't just spectacular. They can influence the evolution of the galaxy itself. They can stir and heat gas, disturb star-forming regions, and affect how quickly new stars can form. So TON 618 doesn't just glow. It participates in shaping its cosmic neighborhood. It's part of a feedback cycle. Matter feeds a black hole. The black hole produces energy, and that energy pushes back on the galaxy that gave it life. Now, let's try something that feels almost impossible to imagine. TON 618 is extraordinarily luminous. Its output is often described as equivalent to the combined light of hundreds of trillions of suns. Not millions, not billions, hundreds of trillions. That's a scale where even most powerful stars in our night sky become irrelevant. And if TON 618 were placed at the center of our Milky Way, replacing Sagittarius A*, our galaxy's own supermassive black hole, you wouldn't just see a bright object. You would lose your night sky. The glow would overwhelm everything. Distant stars would become invisible. Constellations would fade. The Milky Way band that photographers chase with obsession would be drowned out. The light would be so intense, it would essentially erase the concept of dark from a human experience. It would be a blaze, a flood, a constant glare. Not bright like a star, bright like something that shouldn't be allowed to exist. And that's why TON 618 feels like a monster before you even consider the math of its event horizon. Because its brightness alone tells you the engine is beyond ordinary, but the brightness is only the surface story. Every quasar has a darker core. TON 618's black hole has an estimated mass around 66 billion times the mass of the Sun. That number is difficult in a different way. It doesn't just represent large. It represents astronomical dominance. When you compare it to Sagittarius A*, TON 618 is over 16,000 times heavier. Now, the event horizon is the boundary. What scientists call the point beyond which escape becomes impossible. Not because the black hole has a wall, but because the curvature of space-time becomes so extreme that all paths inevitably lead inward. The event horizon of TON 618 is estimated to be on the order of hundreds of billions of kilometers across, often cited around 400 billion kilometers as a rough scale. Now think about what that implies. The solar system, from Mercury to Pluto, fits within that boundary by orders of magnitude, and yet the horizon is still just a boundary around a larger, stranger reality inside, a place where inside itself becomes a concept that doesn't behave like normal human intuition. Now, let's imagine, just imagine that you could stand near it. Not physically, because we can't, but in a conceptual sense, using the behavior of light and gravity we know from general relativity. As you approach, you wouldn't see a simple dark circle like cartoons often show. You'd see something far more unsettling. Around the shadow region near the event horizon, light from behind the black hole can be bent into curved trajectories. This can produce a glowing halo effect, where light wraps around and appears to linger near the edge, forming arcs and rings before it eventually falls inward. Time would also behave differently. Near massive objects, time dilation becomes significant. To an observer farther away, the person near the black hole would appear slowed, almost frozen. Their motion would look stretched, their signals delayed, their timeline smudged across the boundary of eternity, and the light would shift. As radiation tries to escape deep gravity wells, it undergoes gravitational redshift, stretching to longer, redder wavelengths. So what might once appear bright in an intuitive spectrum could become dimmer and more red, eventually shifting toward wavelengths beyond what our eyes can detect comfortably. It would look like the black hole was systematically draining color from a universe. Not metaphorically. Mechanically, physics would make it happen. And after that, there's a singularity, the region we don't fully understand, a place where densities become extreme and our current models break down. It is the limit where human language for reality runs out, and theory becomes an attempt, not an explanation. At this point, you might ask a question that haunts astronomers. How did TON 618 get this massive so early? Because supermassive black holes are expected to grow over long periods. They consume gas, they capture stars, they merge with other black holes. All of that takes time. But TON 618 represents a black hole with enormous mass at a time when the universe was still young. So the usual explanations, growth at a normal pace, struggle to account for its scale. This leads to major questions. Did it start with an unusually massive seed black hole? Did it feed at exceptionally high rates, possibly exceeding what would normally be expected? Was the early universe more favorable to rapid accretion than current models assume? Or did mergers and environmental conditions combine in a way that accelerated its growth beyond current predictions? TON 618 isn't just a black hole, it's a challenge, a puzzle piece that doesn't fit neatly into the box we try to build. And here's the final twist that makes TON 618 more than a cosmic horror. For all its destructive power, it's also an informational goldmine. Because quasars shine across billions of light years, their light passes through matter spread through intergalactic space. That matter leaves fingerprints, absorptions at specific wavelengths. By studying those fingerprints, astronomers can infer the chemical composition of the medium between galaxies, trace how matter was distributed early on, and learn how the universe evolved in its earliest eras. TON 618 is both destroyer and guide, monster in the center, historian in the light. And in the next part, we'll go deeper into exactly what astronomers can learn from it, how the spectra work, what the jets do to galaxies, and what TON 618 teaches us about how the early universe built itself. So stay with me, because TON 618 isn't finished. So we've established what TON 618 is, a supermassive black hole so massive and so actively fed that it powers an intensely bright quasar. But the next question is the real one. How do we know all of this from billions of light years away? Because TON 618 isn't something we can walk up to. We don't get to take samples. We don't get to touch the thing itself. We only get its light. And that light carries secrets, if you know how to read it. When astronomers observe TON 618, they don't just measure brightness. They measure color, but not the color your eyes see. They split the light using spectroscopy, turning the glow into a spectrum like a rainbow of information. In that spectrum, TON 618 shows features that tell a very specific story. Emission lines, bright spikes where atoms are releasing light. Broad lines, signals showing extremely fast gas moving at huge speeds. And patterns that shift in wavelength due to the expansion of the universe. This matters because atoms don't emit random colors. Each element, hydrogen, helium, carbon, oxygen, and others, leaves its own fingerprint. So when scientists see those fingerprints in the spectrum of TON 618, they aren't guessing. They are identifying the chemistry of gas around the black hole, and they're doing it from a time when the universe was far younger than it is today. Now here's a trick. TON 618 is far away, so its light has traveled through an expanding cosmos. As space stretches, the wavelengths of light stretch too. So even if TON 618 emitted a known wavelength, by the time it reaches us it appears shifted, redshifted. toward longer, redder wavelengths. That redshift does two huge things. It tells astronomers roughly how long ago the light left TON 618. It confirms that what they're seeing is indeed coming from a distant era of the universe, when galaxies were forming and evolving rapidly when we say TON 618 is about 18 billion light-years away in the usual distance we observe sense. It's not just a number for scale. It's the stamp of time. It means we're looking at a quasar that was already astonishingly powerful while the universe was still in the middle of building itself. Here's another key point. A quasar doesn't shine because a black hole is on fire. It shines because matter is falling in. And that falling matter becomes a structured system. Most importantly, an accretion disk near the center. The disk is hotter and radiates more strongly at shorter wavelengths. Farther out, it's cooler and radiates differently. So the spectrum becomes a kind of map. By analyzing how the brightness changes across different wavelengths, radio, optical, ultraviolet, X-ray, astronomers can infer properties like how hot the emitting regions likely are, how efficiently matter is being converted into energy, and how intense the radiation environment must be. In other words, TON 618 isn't just very bright. Its brightness is diagnostic. It tells you how ferociously it's feeding. And then there are the jets, those massive streams of plasma launched along the black hole's poles. Jets are important for two reasons. First, they're evidence that magnetic fields aren't just present, they're powerful enough to organize energy on an enormous scale. Second, jets don't stay contained. They interact with gas and the surrounding environment of the galaxy and beyond. Over long timescales, they can heat intergalactic gas, disturb star-forming regions, and prevent fresh gas from settling into galaxy in the way it normally would. So TON 618 is not just a passive lighthouse. It can act like a regulator, pushing back against the processes that would otherwise keep building stars. That's why quasars are often discussed as part of feedback in galaxy evolution. The black hole grows, and its growth can help determine whether the galaxy around it continues growing too. Now, let's clear up a common misconception. Even though TON 618's event horizon is the true boundary of no escape, we don't directly image an event horizon here in the way people imagine with telescope photos. For objects like TON 618, we infer the black hole's properties indirectly from the energy output, the behavior of gas near the center, and models that link luminosity and accretion physics to black hole mass. So scientists are not staring at the abyss. They're reading its effects. But those effects are so consistent, so repeatable across multiple wavelengths, that we can build extremely strong conclusions about mass, power, and structure. Let's return to the scale question, but with a different angle. The black hole mass is estimated around tens of billions of solar masses, often quoted near 66 billion. And that's where the how did it get so big so fast mystery becomes terrifying, because black holes grow through processes that, according to many models, should not be able to reach that size early enough unless something unusual happened. This is where astronomers debate scenarios like a massive initial seed. The black hole didn't start small. Extremely rapid growth. The environment in the early universe might have provided unusually large amounts of gas. Superficial feeding. Accretion might have been able to proceed at rates higher than typical limits, at least for periods. Frequent mergers. Galaxy interactions can bring black holes together, allowing them to combine and jump in mass more quickly than simple feeding alone. TON 618 becomes a stress test for cosmic history. If it can become this massive early, then either the universe was better at feeding black holes than we assumed, or the black holes themselves were born in a way we haven't fully accounted for. Now comes the part that turns TON 618 from a horror story into an education tool. Because quasars don't just shine through empty space. Their light travels through clouds of gas that lies between galaxies and stretches across intergalactic space, and that gas absorbs certain wavelengths. So TON 618 spectrum carries not only information about the black hole's immediate surroundings, but also information about the universe it passed through. That means astronomers can learn about the chemical composition of the intergalactic medium, how matter is distributed on large scales, and how the universe's structure matured during that early era. In a way, TON 618 works like a cosmic flashlight, and the dust, gas, and filament-like structure of the universe are what produce the shadow patterns that tell us what the light encountered on the way. So why do we study TON 618 so obsessively? Because it's both a challenge to our models of how supermassive black holes form and grow, and a tool for mapping the conditions of the early universe. It's a reminder that the cosmos doesn't care whether our expectations feel comfortable. If the universe found a path to grow objects like TON 618 quickly, then our job is not to ignore it. Our job is to understand the path. And every new observation, every spectrum, every wavelength measurement, every jet study tightens the puzzle. At this point, we've covered what TON 618 is, where it sits in cosmic time, and how astronomers read its story from spectra and redshift. But that still leaves one unsettling question hanging in the air. How does a black hole, something that should be completely dark, produce a display bright enough to outshine galaxies? And even more terrifying, what happens to the galaxy around it while it's doing that? Because TON 618 isn't just shining. It's transforming its environment over and over, like the universe running a violent engine in the middle of its own construction site. When we say TON 618, we often picture a single black hole, but a quasar is more like an orchestra. The black hole is the conductor. The accretion disk is the stage. The gas around it is the instruments, dense clouds, fast-moving material, ionized plasma, all responding to the black hole's pull and its radiation. So the brilliance we observe comes from multiple regions, not just from the event horizon itself. The black hole's gravity sets the accretion disk spinning. The disk heats up, and as it heats, it radiates, first in ways that match the disk's temperatures, and then in ways that spread outward and excite gas far beyond the disk. In other words, the quasar is a power plant built out of infalling matter, not because the black hole burns, because gravity forces matter into a state where energy release becomes unavoidable. Picture a spiral of matter, not a neat galaxy spiral with beautiful arms. This is matter forced into a thin, rotating structure by gravity. As it spirals inward, the material gains speed, and faster motion means stronger heating when that motion interacts and dissipates energy. Inside the disk, temperatures can climb to extreme levels, and different layers radiate different portions of the electromagnetic spectrum. So if you zoom in conceptually, the disk becomes a gradient. Inner regions, hotter, emit higher energy radiation. Outer regions, cooler, emit lower energy radiation. That's why quasars can be bright across radio, optical, ultraviolet, and X-rays. They aren't one-color objects. They're broadband engines. And TON 618, be among the most luminous, signals that its accretion process is not timid. It's intense. It's efficient. It's feeding at a rate that makes the universe light up. Now imagine the black hole and disk are inside a chaotic galaxy environment. Clouds of gas nearby, dust, fragments left over from mergers. And in front of all of it, the quasar's radiation. Quasar light isn't just bright. It's energetic enough to ionize gas. Ionization means stripping electrons from atoms, turning neutral material into charged plasma. That matters because charged and excited gas then emits its own characteristic radiation, including the emission lines we detect in spectra. So when astronomers look at TON 618 spectrum, they aren't only seeing the disk, they're also seeing the way the quasar reaches out and changes the state of surrounding matter. This is one of the reasons quasars are such rich sources of data. They don't just exist. They imprint themselves onto nearby gas. They write their presence into the spectrum like a fingerprint left on glass. Spectra of quasars often show multiple sets of features, sometimes referred to as broad and narrow emission line components. Broad lines correspond to gas moving at tremendous speeds, close to the central engine. Narrow lines correspond to gas that is moving more slowly, farther out, in regions where gravity still influences motion, but not at the same extremes. So in a sense, the quasar spectrum contains a spatial clue. Even though we can't resolve the structure like we would a nearby object, velocity information helps reconstruct which parts of the system produce which signatures. That's how astronomers go from a distant point of light to a complex physical machine operating billions of years ago. Ton 618 is not merely a beacon. It's a laboratory happening in deep space, with the universe acting as a detector. Now let's talk about the jets again, but with more focus. Jets are strongly linked to magnetic fields and to how the accretion disk, the black hole's environment, and possibly the black hole's rotation all interact. The big idea is the central region twists magnetic structures into configurations that can launch plasma outward along preferred axes. Those jets travel long distances because they can remain collimated and energetic for enormous times. And because the jets carry energy, they do more than look spectacular. They interact. They heat gas. They can disturb the surrounding medium on large scales. Over time, that energy input can change whether gas cools and collapses into new stars. That's why quasars are discussed in the context of feedback. Feedback means a black hole's activity doesn't stay local. It pushes back on the galaxy's growth. It can either regulate how quickly a galaxy forms stars, or in some cases suppress star formation, depending on the conditions. So TON 618 is not just a bright center. It's a dynamic driver of galactic evolution. Here's the part that makes TON 618 particularly unsettling to astrophysicists. TON 618 exists at a time when the universe was young, when galaxies were rapidly building themselves, when mergers were more common, when gas was more abundant and denser than it is now. In that environment, black holes would have more fuel available. But more fuel still doesn't automatically explain everything. Because to reach an estimated mass on the order of tens of billions of solar masses by that early era implies unusually fast growth. And growth isn't only about having gas nearby. It's about how efficiently that gas can be captured and converted into energy through accretion over time, and how often a black hole can keep feeding without being starved. So TON 618 forces researchers to ask, was the starting seed unusually massive? Did it grow through repeated mergers of black hole systems? Were feeding conditions more extreme than our standard models assume? Did some combination of environment plus accretion physics allow it to expand faster than expected? The universe can be generous with surprises, but it's still expected to follow physics. TON 618 is one of those rare objects that makes the physics feel stretched, not broken, just stretched to the edge of what we currently think is likely. One thing people sometimes overlook is that quasar brilliance is not necessarily permanent. Black hole feeding can be episodic. A quasar might turn on when fresh gas flows in. It might fade if the fuel supply drops. Or it might flicker due to changes in the accretion flow. We don't just have to explain how TON 618 became so massive. We also have to explain how long it remained powerful enough, long enough during that early cosmic chapter for it to be detectable to us at all, because we don't observe it continuously. We observe it as a specific moment in its history, as viewed through billions of years of travel. That means the existence of TON 618 as a quasar is already a clue about how quasar activity cycles might operate in the early universe. And if quasars can be driven in repeated bursts, their collective impact across cosmic history could be even greater than we estimate from average activity levels. Let's bring that Milky Way replacement idea back, but this time in a more unsettling way. If TON 618 were placed at the center of our galaxy, its radiation wouldn't only brighten the sky. Depending on how we define distance and the scaling of intensity, it could overwhelm observational detail. And if it were active with similar energy, it would alter the conditions around a galaxy's central regions. Even if the details of star-by-star disruption are complex, the conceptual point is straightforward. A quasar is a high-energy environment. It's not just bright. It's a barrage of radiation and charged particles over huge spatial scales. So the darkness we normally rely on as a background for observing the universe would disappear. But more importantly, the quiet balance of a galaxy would be disturbed. A quasar is a reminder that cosmic structures aren't passive. They are powered. They push. They reshape. Now we reach the philosophical core, but we keep it anchored in science. TON 618 is a destroyer because it consumes matter and can influence star formation through energy feedback. It's a guide because the light it emits travels across intergalactic space and carries physical information. This isn't mystical fortune-telling. It's physics. That light passes through matter, and that matter absorbs and alters specific wavelengths. Those changes tell us about chemical composition, distribution of matter, and conditions in the early universe. So while the quasar is violent at its center, it becomes a kind of record keeper during its journey outward, a record encoded in spectra, a record written in absorption lines, a record we decode with telescopes and models. TON 618 is both the event and the message, the monster and the archive. And so what do we really learned? We learned that TON 618 is a system where gravity converts matter into energy with extreme efficiency. We learned that its brightness is due to accretion and radiation, plus jets and magnetically driven outflows. We learned that its existence so early in cosmic history challenges straightforward growth scenarios. And we learned that its light helps astronomers reconstruct the early universe's composition and structure. TON 618 isn't only a big black hole. It's a key to understanding how the universe built its brightest engines and how those engines shaped the galaxies around them. So we've walked through the basics. We know TON 618 isn't a normal star, not even a normal galaxy. It's a monstrous black hole about 66 billion solar masses, feeding so violently that it lights up the universe as a quasar. We know its brilliance is powered by infalling matter, compressed into an accretion disk, heated to extremes, producing radiation across the spectrum. We know its jets can blast outward for millions of light years, carrying energy so enormous they can influence the galaxy around it. And we know we don't observe it like we'd observe a planet. We observe it through its light, stretched by distance, imprinted with physics, and decoded by astronomers. But here's where the story becomes bigger than one object, because TON 618 doesn't just show us a single black hole. It shows us the early universe behaving like a different world. To understand why TON 618 is so important, you have to understand the environment it lives in. Billions of years ago, when this quasar's light began its journey, space wasn't empty and quiet. Galaxies were colliding more frequently. Gas was denser. Mergers were common. Star formation was more intense. And the raw ingredients needed to grow massive objects were everywhere. So when a black hole like the one in TON 618 starts feeding, it doesn't have to wait forever for fuel. It can find fuel. It can feed rapidly. And because quasars can stay bright while accretion is strong, TON 618 may represent one of those rare moments when a galaxy's center becomes a full-on engine, a galaxy in its most violent phase, a time when the universe was still assembling itself, fast, messy, and powerful. Now let's return to something subtle but crucial. TON 618 is so far away that its light has traveled for around 18 billion light years, in the way we express observational distance today. That means it carries information not only about what's happening near the black hole, but also about what the light passes through on its journey. As the quasar light moves through intergalactic space, it encounters clouds of gas, hydrogen, helium, and trace heavier elements. And those atoms don't just let light pass. They absorb specific wavelengths. So in the quasar spectrum, astronomers see absorption features, gaps and dips in the spectrum, at precise energies. Those features act like a chemical barcode. They tell scientists what elements were present, how much gas existed along the line of sight, how that matter was distributed in the early universe. In other words, TON 618 is not only a beacon, it's a detector. The quasar becomes a flashlight shining through ancient cosmic material, and the universe answers back in wavelengths. Astronomers also use quasars like TON 618 to study the cosmic web, the vast network of filaments and voids formed by gravity. Even though the universe looks empty to the eye, matter is clumped on enormous scales. And because TON 618's light passes through that large-scale structure, the pattern of absorption tells a story about where gas exists, where it doesn't, and how structures evolve over time. This is part why TON 618 is so valuable in cosmology. It lets researchers test ideas about how the universe expands, how quickly structures form, and how matter transitions from early clumps into the organized galaxy networks we see later. So TON 618 is not just astrophysics drama. It's also cosmological evidence. It helps us verify models of how the universe became what it is. Here's another reason TON 618 matters. A quasar doesn't stay isolated. Its energy output, especially when you include radiation and jets, can interact with the gas surrounding the galaxy's core. That interaction is often described as feedback. Feedback means a black hole's activity influences star formation in its host galaxy. Depending on the conditions, feedback can heat gas and prevent it from cooling into new stars, drive outflows that remove star-forming material, or compress some regions, changing star formation patterns. So the black hole and the galaxy aren't separate stories, they're locked in a long-term relationship. One feeds the other, until the feeding becomes a thing that limits what the galaxy can do next. TON 618, at its early stage, is one of the clearest examples of how intense that relationship can become. The center of the galaxy isn't just a place. It's a force shaping the future. And yet, even with all this, the biggest question remains. How did TON 618 grow so massive so early? Because if a supermassive black hole reached something like 66 billion solar masses when the universe was still relatively young, then standard growth timelines can feel too slow. So astronomers keep refining scenarios such as unusually massive black hole seeds formed early, extremely efficient accretion episodes, repeated mergers during frequent galaxy interactions, periods of near maximum feeding in the dense early environment. But best explanation isn't the same as certain explanation. TON 618 sits at the edge of what our models can confidently account for. It's like a cosmic riddle carved into light. Every new observation tightens constraints, but the final answer still isn't fully written. That's why it keeps showing up in research papers, telescope proposals, and theoretical discussions. Because TON 618 is a stress test for our understanding of black hole growth. Now, about the event horizon, about that boundary where nothing escapes. In your script, you describe it as roughly 400 billion kilometers across for TON 618's estimated mass. That's an astonishing scale. But here's the uncomfortable truth. Even with powerful telescopes, we don't directly image the event horizon of TON 618 the way we can with closer black holes. For TON 618, the event horizon is inferred. Scientists build models that connect, observe luminosity, gas dynamics, spectral signatures, and general behavior expected from accretion physics. So the horizon itself remains hidden, but its existence is supported by the behavior we observe. Like you can't see the deep ocean trench directly, but you can still know it's there because of what the water does around it. TON 618 is the same kind of certainty, strong, indirect, and hard-earned. Finally, there's something emotional, something hard to measure. When we observe TON 618, we are not only seeing a distant object, we are seeing an ancient moment, an epoch when the universe was still constructing galaxies in real time. So every time a spectrum is recorded, every time a jet is analyzed, every time a light is traced to the cosmic web, we're doing more than gathering data. We're witnessing the universe in the middle of its building phase, a time when black holes, quasars, and galaxies weren't mature yet. They were alive with rapid change. And TON 618 is one of the brightest, most extreme snapshots of that era, which means TON 618 isn't just terrifying, it's enlightening. So here's what TON 618 ultimately teaches us. It teaches us that the darkest objects in the universe are not silent. They speak. They speak through radiation. They speak through spectra. They speak through the way galaxies evolve. They speak through the way the early universe leaves fingerprints on light. TON 618 is a destroyer because it consumes, because it can blast away gas, because it can reshape the destiny of star formation around it. But it is also a guide because its light becomes a map of early cosmic chemistry, a map of structure formation, a map of how the universe learned, over time, how to grow. So when you look at TON 618, you're not only staring at a black hole, you're looking at the universe revealing its secrets from the moment those secrets were still being made. And that's the real horror. Not just that it exists, but that it existed so early, and that we can still read its message today, across billions upon billions of years of distance, across the silent expansion of space, across the darkness. And in that darkness, there is light enough to change what we believe about the cosmos.